Evidence of electromagnetic radiation emission. This is a strong evidence of an chemical phenomenon. This is the X-ray film that was placed in contact with the cell 4 after 552 hours from the beginning of the experiment. The duration of exposition was 7 days. The film was then analyzed by microdensitometry after calibration with a standard X-ray camera. The three-dimensional representation of this film show practically what appears on the film on the ZX plane, while the exposure value is shown on the Y-axis. In other words, this is the blackening intensity of individual spots. Now, there are a number of questions that need to be answered. Why an exposed region between spots? Why spots? This will be treated after in the slide A, B, and C. What is the energy of the radiation? How much total energy was released? What is the nature of the radiation? And finally, it should be remembered that the same type of film that wrapped the white cell was not exposed. Why spots? To explain the presence of spots in the film, the position of all systems components relative to X-ray film must be considered. The figure shows the simplified plan diagram of the arrangement of the cells, and in particular not only the position of cell 4 with respect to the film, but also and above all the arrangement of the internal components of the cells. The cells were contained in a perspex torus in which thermostated water circulated. The torus was itself inside the neutron detector. In the same figure, there is a table listing all the materials with their respective thicknesses and densities, starting from the palladium cathode up to the inner wall of the outermost circumference of the torus. The usefulness of the data in the table will soon be understood. The scale drawing shows the position of the cell with respect to the film and in the center of the torus. It's important to observe the position of the cathode, which you remember is a bundle of palladium wires. At the center of the cell, with respect to the 1 mm diameter platinum rod, represented in plan view by the green circle, which supports the cylindrical platinum network which forms the anode. For simplicity, neither the cathode nor the anode are shown in the figure. If the cathode emitted the radiation totally absorbed by the platinum, but completely transparent to the other surrounding materials, this would produce a shadow cone such as to obscure all the emissions generated in that solid corner. The distance between the two nearly parallel sets of spots measured on the film is 7 mm plus or minus 0.05 mm. Why an exposed region M between spots? As we have already seen, the measurement of the exposed area between the spots made directly on the film is 7 mm. The calculation can be made from the geometry of the system, and the value of 7.67 mm is obtained. So a ratio between the two values that differs by about 9.6%. This difference is due to the shape of the cathode, the respective positioning of the electrode, which modifies the value of the distance f between the anode and the cathode. Furthermore, following the electrolysis, a deformation of the electrode is created. Shown here is the cathode of the cell 4 after 952 hours experiment compared to the electrode before the experiment. The X-ray film was analyzed with a microdensitometer with steps of 600 microns on the z-axis and 50 microns on the x-axis. The measurement of the optical density of the spots in Röntgen exposure units took place by calibration with known exposures of the same type of film and developed with the same procedure. White spots, Section A. The shape of this and distribution of the spot is not compatible with palladium X-ray diffraction. To obtain this, a source having an energy of 21.61 kV is needed, and in the system under examination, the maximum energy involved is the potential difference between the electrodes, which is the order of 3 to 5 electron volts. Are the material interposed between the palladium cathode and the X-ray film capable of fully absorbing this radiation? This can be verified by making a fairly simple calculation, as long as you know the interposed materials, their thickness and their density. The thickness corresponds to the optical path of the radiation. It's necessary to know the dependence of the photon energy of the respective mass absorption coefficients. The intensity of the transmitted radiation I, with respect to the incident 1 I0, is given by this relation written in red, where ρ I is the density of an ith material. The figure shows that at the K threshold energy of palladium, only the interposed material, even without palladium, would completely absorb the radiation. In fact, we see that at 21.61 kV on the YPD curve, at that energy, the transmitted intensity is 0. Therefore, it means that the interposed materials would totally absorb that radiation. As an example, if we put ourselves at 150 kV, the presence of a thickness of 875 microns of palladium would attenuate the radiation by 50%. White spots, Section B. Findings and hypotheses more compatible with the spot structure. Outside the shadow cone, the radiation source cannot be on the surface of the electrode because this would produce a diffuse and a no-spot blackening. Let us consider the multi-wire structure of the cathode, in particular of a cell 4 made of 150 wires of 250 microns in diameter. This structure can be represented as in the figure and is presented as a pseudo-HCP structure with 7 shells. The optical path of the radiation, whose source is inside, may or may not be formed by slits. In path A or path B, the two optical paths are distinguished by situations of reduced or total attenuation of the radiation. The total case is that of path B. The most realistic hypothesis is the presence of multiple point sources on the surface and or inside some wires, but not in the outer ones. The system is therefore a set of virtual slits which are illuminated by the radiation according to its angle of propagation. The existence of such slits is in the domain of the shortest palladium optical paths. The existence, positioning, and the intensity of the spots depends on the domain of the slits, on the positioning of the sources, and on the optical path, as well as on the energy of the radiation. The figure shows the attenuation value of a radiation of 90 kV if the source were at the origin of a coordinated, expressed in microns at 0.0 or at 433 and 750 of the HCP structure in another shell, that is the fourth shell. In the latter case, the attenuation is lower because the optical path is shorter. The optical path associated with each spot is obtained from the microdensitometry measurement of the film, known the geometry structure of the system. Here, the calculation is represented by this equation written in red, where Lthi is the x-coordinate of the ith spot measured from the central axis between the two spot distribution. White spots, section C. The figure compares the real distribution of the spots with the distribution calculated through the simulation. As we see, there is enough correlation between the real and the calculated situation. The relation to the position of the film with respect to the cathode and the previous equation, it's possible to estimate the position of the sources which generated the spots on the film. This is represented by the red dots in the figure. It should be noted that none of these are found in the outermost wires, and the major densification is in an intermediate region of the HCP structure. It is evident that the distribution of the sources is expected to be uniform. The representation shown here was obtained in relation to the positioning of the X-ray film with respect to the cell.